Hi, I'm Edward Ding, and I am the Vice President of the Electrical Subdivision here at AVBots. Today, we're going to talk a little bit more about sensor optimization.
Hey guys, my name is Phoebe Tang, and I am the Vice President of the Software Division.
Hi, my name is Justin Yu, and I worked on benchmarking various hardware configurations.
Hi, I'm Craig, and I worked on developing vision and navigation code.
Hi, I'm Vincent, and I worked on benchmarking vision models and planning out a new sensor network overhaul.
Hi, I'm Nikhil, and I worked on implementing the music algorithm for the hydrophones.
Hi, I'm Angad, and I worked on implementing a water current into our simulator and testing our hydrophones algorithm.
So we use a couple of different sensors in our submarine. The first one is the AHRS, or Altitude Heading Reference System. It measures the pitch, roll, and yaw of the submarine. It's similar in function to an IMU and works by measuring the acceleration on several different axes of the submarine. This can be crunched down into locational data, which can better help us understand where the submarine is. The Doppler velocity log is a device that can be used to find the acceleration of the submarine. It is used to augment the data from the AHRS to give a better idea of where the submarine is in the pool. It can also be used to find the distance between the submarine and the bottom of the pool. The pressure sensor is used to measure the pressure of the water on the submarine. It can be used to determine the depth of the submarine.
Our submarine has two cameras, the front camera and the down camera. Both cameras are accessed by our software team to have a better view around Nemo. We use a graphics computing unit, or a GPU, to process information from sensors from all around Nemo. We use a GTX 1080 Ti from NVIDIA because of its amazing computing performance. Another important sensor that we use is the hydrophones. The hydrophones work in conjunction with the DVL to discern depth with data from the pressure sensor. This sensor has tons of possibilities that our software team is currently researching.
Last year, our competition strategy was to reduce the amount of tasks to simplify our approach. However, our navigational method was not entirely accurate, which led to missed bin drops. This year, we focus on increasing the accuracy of navigation by refining our vision and sensor system. Now we have a problem. So images taken underwater are distorted by a blue-green filter, which takes away pixel values of the image. And this is detrimental to our sub's vision, creating difficulties such as the inability to recognize gates. In order to fix this issue, we used OpenCV, a software tool that helps process images. There are a couple of steps to the algorithm. First, convert the image into map format, which makes it easier to work with. Second, find a high and low percentage pixel value of the image. Third, do a few calculations to each pixel of the image. And finally, normalize the image and redraw. This algorithm increases the accuracy of the sub's vision and allows the sub to see further.
So this year we've also decided to upgrade our machine learning model that we use for object detection. So previously we used faster RCNN, which was bulky, slow, inefficient, and took a really long time to detect objects in the camera. And it needed a really heavy GPU to run that not a lot of our members possessed. So this year we've decided to switch to EfficientDet, which is a lot lighter, a lot faster, and it doesn't need heavy GPUs to train or use. So this has also allowed us to detect objects at a much faster rate, allowing the sub to reposition itself with more accuracy above objects like the bin.
This year, we also began research into replacing our aging legacy microcontroller and sensor system. We frequently found ourselves running against hardware limits when we were trying to upgrade our navigation and sensor stacks. To remedy this issue, we planned out a complete overhaul of the low-level sensor and control system based on a distributed philosophy. Our new planned system has several distributed microcontrollers handling different sensor inputs, all hooked up to a central CAN network. This system is much more flexible than our old system with a single central underpowered microcontroller, allowing us to upgrade and add new sensor, navigation, and processing components easily to the system. The team plans to continue implementing this system over the next year, while continuing to analyze weak points in our sensor and control system.
In previous years, we used a discrete Fourier transform to estimate our bearing relative to the pingers. However, part of this algorithm was choosing between one of two roots of a quadratic equation, which caused an error rate of 5%. This year, we increased the accuracy of our hydrophones by migrating our angle of arrival estimation algorithm from a basic Fourier transform to the multiple signal classification or music algorithm. We calculate the time delay between the first element in the hydrophone array and each successive hydrophone. We use the time delay to calculate the steering vectors of the Pinger's sound waves and compute a covariance matrix. We then pass this covariance matrix into the music algorithm, which determines a specific value for each angle measure in a spectrum ranging from between 0 and 180 degrees. The peak of this spectrum is the most probable angle of arrival, which we then use to turn to the octagon.
So with all of our sensor optimizations, now it's time to talk about our confidence ratings. So for us, it's 80% for gate, 80% for buoys, 55% for bins, and 25% for octagon. So it's high for gate and buoys because of our improved vision system allowing us to track objects accurately. Next, bins is slightly lower because of our clunky navigation code. And finally, octagon is the lowest because our hydrophone system is not fully implemented yet.
This year we're using newer and more efficient vision systems like EfficientDet and Yellow V5. We want to find the best hardware configuration for these vision systems while drawing the least amount of power. Therefore, we tested various GPU/CPU configurations to see how they perform. In this spreadsheet here, we took notes on the different hardware configurations, and we learned that we no longer need a GTX 1080 Ti to run the models, which helps building Submarine easier because we don't need such a large GPU to run the models.
So previously, for testing our sensors, we would often use pool tests, but pool tests were often prone to hardware failures, making it difficult to test. And then furthermore, in the pandemic, we were even unable to hold pool tests. So we built an end-to-end simulator instead so that we could test our sensor input, which is fed into our navigation software. So the simulator is implemented in Gazebo with DVL, IMU, pressure, and camera sensors all implemented with noise.
Since the simulator had no water current, sensor readings were too perfect, causing the sub to perform better than it would in a real-life pool. To fix this issue, a water current was implemented into the simulator such that it resulted in even more turbulence than that of a real-life pool. With this, we could better judge the sub's ability to handle turbulent conditions, as if it could perform tasks successfully in an extremely chaotic simulator, it would continue to perform them well in a more peaceful pool.
So because of our simulator, we've been able to test our vision and navigation code, which relies on camera sensor input. So for example, we've devised a new method of aligning the sub above the bins by continually readjusting the sub's position. So this works by utilizing the submarine's down camera, detecting the bins, which we can use to calculate how much the sub needs to move in order to get right above the bins. So because often one calculation is inaccurate, then we put this in a loop so the sub continually readjusts itself until finally it accurately stations itself above the bins. So using this method, we've been able to elevate our bin straub accuracy from around 40% to around 80% in the simulator, which is huge and I hope will help us in the next competition run. Plus, the simulator also allows us to find new ways to use our current sensors. So for example, our submarine doesn't have a sonar sensor, so previously we were unable to get the distances to competition objects. So instead, now we've tested a new method in the simulator which uses camera properties such as focal length and sensor size to calculate the distance to an object. And in the simulator, it showed to be within 1 or 2 meters of accuracy. So this was a huge upgrade for our submarine because it allows us to approach competition objects a lot more intelligently, because we know the distance to the object, which in my opinion makes our submarine look a lot more stylish, and hopefully it'll allow the submarine to function a lot more smooth when we resume in-person testing.